Good afternoon, everyone. I'm Hao Wen from Computer Science Department of University of Surrey. Today, I'm going to give a talk about machine learning for efficient experimentation, the asynchronous batch search strategies for self-driving laboratories. It is a joint work with Jacob Littler and Conor Rupnow. Automation is ubiquitous in various domains, including physics, chemistry, and biology. For example, when we making the alloys, chemicals, paints, etc., and they all involve automations. Take the coating as an example. Coating are crucial for clean energy technologies. For example, it can be used in energy capture, such as the solar cells, and it can also be applied in energy storage and conversions, such as the batteries, and also it can also be used in the energy conservations. For example, the smart windows. When we making the coatings, there is a autonomous technology named as the self-driving laboratories. So here is the device to make the coatings. There are several stages. For example, in the first stage, we prepare the samples and then loading, and then do the spray coating, and finally in the releasing stage. It can be summarized in these diagrams. There is a robot arms moves experiment from stage to stage. So the question is that how to minimize the experiment time and maximize the conductivity of the coating. The conductivity of coatings depends on several factors. Here there are 7 factors. For example, the precursor concentration, and the sample content, flow rate, speed, and etc. How to maximize the conductivity of coating by manipulating these factors simultaneously. Next, I will give a formal definition about this problem. The first is the search space. There are several candidate choices for the inputs. And the next is the objective functions, which is unknown to us, and it is the exact expression for the objective function is unknown, and it is quite expensive to evaluate the objective functions. And the third is optimization problems. How to find the candidate input with highest output. The naive strategy is that we can using the random strategies, which is doing the experiment by trial and error. Can we do better? Bayesian optimization is a machine learning model, and it gives a surrogate statistical model and uses to search the input space intelligently. The basic idea for the Bayesian optimization is it replaces expensive queries of the objective function with cheaper acquisition functions. Since there is also observation noise for the objective functions, it is better to also model the uncertainty of the model. There are 3 components for the Bayesian optimization. First is the statistical model. The Gaussian process is a common choice to build the statistical model. And the second is the acquisition function, which is a metric to select the next sample points. For example, the expected improvement. And the third is the optimizer for the acquisition functions, such as the local search. As some of the audience maybe haven't used the Bayesian optimization before, so I will first give a brief introduction about how the Bayesian optimization works. Here, the yellow dashed line is the target objective function, and there are the black dots are the initial samples to train the Bayesian optimization, and the green, the blue line is the mean of the prediction of the Bayesian optimization, and the shaded area is the standard deviation of the output. First, we train the Bayesian the statistical model using the initial 2 samples. In the red figure is the analytical expression for the acquisition function. When we maximizing the acquisition function, we found that the 2 is the next point, which means that it has the highest acquisition function value, and that is the points we want to evaluate. But unfortunately, the value we obtained is small, and we update the Bayesian the Gaussian model, and then maximizing the acceleration function. It gives the value between 0 and 0.5. Then we test the sample points suggested by the acceleration function. The iteration goes one iteration by one iteration. Finally, it can find the optimal inputs with the highest output value in the iteration 7. This is basically how Bayesian optimization works in toy examples. However, Bayesian optimization is a sequential algorithm. It means that the optimization of the Bayesian the Gaussian process only begins when the experiment has been finished. It means that take the figure B as example. It's when once experiment finished, then it begins to another experiment. Can we do better to make better use of the wait time when we doing the evaluation of the experiments? That comes to our proposed algorithms, which called asynchronous batch Bayesian optimization. It can be summarized in the figure 3. As compared to the figure B, we can see that in the iteration 5, there are already several experiments being evaluated, which is called the pending points. We can, during the evaluation of the first experiment, we can also doing several other experiments. This whole framework it can be summarized into the asynchronous batch Bayesian optimization. The delayed feedback is called as the pending points, and there are several such strategies. First is the noisy expected improvement. It considers the pending points into optimization, and the second is the mode cycling, which mode between confidence bounds and the space filling algorithms. It is baseline algorithms shown in last year NeurIPS paper. And the third is the classic expected improvement with analytical formula accounting for the pending points. The fourth is the random strategies. This is the experiment results. In the left figure, we report the metric for the accumulative regret, which is the output value towards the difference between the output value towards the global maximums. As we can observe, the proposed QNEI in the central columns have the lowest accumulative regret. And the red figures summarize the iteration process during the optimization of the Bayesian, asynchronous batch optimization. The top line is the QNEI without delay, and the green line is the QNEI with delays. Comparing to the counterparts, the QNEI performs better. So in conclusion, we propose a synchronized batch such as strategy to improve the experiment efficiency and the performance. And the second, we build a simulator for the self-driving laboratory to test such strategies. And the third, we invest the influence of delay time and dimension of such space. The work has been accepted in this year's Europe workshop on AI for materials. Thank you all for your attention. Do you have any other questions? Okay.
Thank you. That was great. So pipelining, you do what every processor does, which is stack things to run together. Could you explain, could you go back to your chart where you had the regret thing? Oh. So I'm just interested to know, A, the difference between the delay and no. Yeah, that's one. So two things. You don't on that graph have serial, do you, by comparison?
The serial case is shown without delay. So
that's the no delay one, fine. So my question is, what's the difference between the delay and no delay? And that's serial in effect. But this is going to take a lot longer with the no delay because they aren't overlapping then, I guess.
I think within the 50 iterations, there are still some gap, but in the long run, they should achieve the same observation value.
So I think I'm misunderstanding. Maybe we should stop. But one of the things you're looking at is how much lab time you need to take to converge to your result. And your whole thing about overlapping and pipelining like a processor does is to get there quicker. And in return for which you're giving up some predictability by doing this overlapping thing. I just wanted to know, on this same graph, and maybe I've misunderstood, if you plotted real time on the graph, not number of observations, how long would it take for serial, the original serial, to converge?
Since we don't have the real robots, this is just the simulation. Yeah, we don't actually report the actual time.
Okay. But it sounds like it would be 3 times longer considering there's a conversion pretty well, or 4 times longer. So,
okay.
Can we go back to the search strategy of the iterations? That's
This one?
I've looked the iteration 4. The uncertainty is too different with the 3 and the 5.
yes,
The uncertainty of the iteration 4 it's too different with the iteration 3 and the iteration 5. You can find that
the acquisition function is rebuilt. So after in the iteration 4, there are already 5 samples. So the acquisition function is updated. So it should be different in different iterations.
But that means for after 4 iterations, the strategy is not very precise to prediction for the next experiment point.
I think it is not related to the precision. It is just in iteration 4, for example, it just consider the history of data and try to build a surrogate model, and it is a metric to evaluate what is the last sample points should be.
What I consider is that if we don't have enough materials to do the experiment, if I only have 4 iteration, but if you plot that prediction of the real function, that maybe is not very precise to predict. I think so. That maybe not cannot use to the real world to do the experiment. I think that.
It's a known problem with Gaussian processes because they don't like the scaling of the covariant matrix. And in this case, the parameters, hyperparameters, so-called hyperparameters of the Gaussian processes.
Okay.
It's a bit of a shame that you run out of samples.
Yeah. Okay.
So I think maybe the difference in paradigm is that if you're just predicting, then iteration 4 doesn't look useful. But we're not just predicting, we're predicting to make a decision to then get to iteration 5. And you see iteration 5 obviously looks intuitively more better. So at times, we always, as Hao said, we always retraining the surrogate model with the new data point. And sometimes it would look really weird, like iteration 4. But it's not about, looking weird at one point. It's that as you go along, you can see that in iteration 7, for example, we converge to a better point. So it's not about, the surrogate model is very important. Because the better it predicts and the better the uncertainty is calibrated, the better the Bayesian optimization can be. But at times when you have interesting constellation of data points, you will get a surrogate model that doesn't look intuitive or useful for prediction. But it's not used for prediction as the goal; it's used for optimization as the goal.
Okay.
And so what you see, for example, here, you said it with the hyperparameters, is that the hyperparameter optimization chose to use very squiggly lines, right? So it sees that basically it's reverting to the mean. So Gaussian processes are a Bayesian model. So you start out with a prior guess of what it is. And so here the prior guess is that it's 0. And then the way we optimize the hyperparameters, or the hyperparameters were chosen, is just saying that, oh, if you don't have data points, just go back to 0. Yeah. And that's why it looks like that. And that's why we have, extreme small uncertainty around the data points, and everywhere else it's extremely high. But that's just a temporary model, right? Then we move on to iteration 5, iteration 6. And so I wouldn't be worried too much about it. If you stop at iteration 4 and you're making predictions, yes, then you want to look maybe at what exactly the hyperparameter choice here was.
And I guess you could look at something like your cumulative uncertainty.
Yeah.
The area inside that's at least clearing, clearly that's higher than on the previous 3 iterations. So if I'm stopping there, I would ignore iteration 4 and go back.
It depends how you want to do your modeling choices. There's an even more pressing problem, which is that this is a one-dimensional thing. If you go 4 or 5 dimensions, we can't even plot this. So we would never actually see this weird behavior.
But you might be able to do the cumulative uncertainty or something.
Maybe something like that. I haven't thought about that, and I see the intuition there. Yeah. But yeah, so
16 dimensions. Yeah.
Yeah. So long story short, this is expected behavior, and it's not problematic behavior if you're using it for sequential optimization. Yeah.
So it's a very interesting approach to hybridize Gaussian processes. Well, essentially based on optimization with space filling designs. I'm just wondering what kind of space filling designs you're using and how you're hybridizing them, how you're switching between the two.
So the space filling algorithm means that it says the points which has the farthest distance comparing to the samples which were available. Since motorcycling is user-defined search strategies, it incorporates some prior knowledge in the production of coding. The optimal hyperparameters, when making the coding, lies in the corner of the bounds, so in the left or right corner of bounds. So the space filling algorithms just pick the farthest points comparing to the existing input value and
pending ones, I guess.
Yeah, exactly. Yeah,
Is
that is
that
the user-defined strategy.
Is that why I went for 2 in the first round, because it's extreme? Why is that? Did that contribute to this acquisition function or iteration 1?
Purely uncertainty.
Okay.
Because if you
fine, just the uncertainty. Fine.
Yeah.
Yeah, but sorry, yeah, that is not space filling, yeah.
No,
so
it could have, but that would be another reason to go to the extreme. Right?
Yes. So are you saying that the space filling part is user-defined, essentially?
Yeah.
Okay, so you're not using any.
So we have prior knowledge that the better we lies in the corner of the input space. So we always select the farthest points to the.
Yeah. But in the general case, you wouldn't have that knowledge,
yeah.
So what do you do in the general case?
I think maybe to avoid some confusion here as well. So so this is the robot setup you see on the left here. That was built by material scientists and roboticists and stuff like that. They just used off-the-shelf Bayesian optimization. And what they then encountered is that, as you see here in the 0 operation, if you have 4 steps and you do the red one and you do the yellow one, let's say you want to throw something into the red one, if you're using expected improvements of a closed form acquisition function, it will give you the same experiment again because we haven't received a new one. So what they came up with is something called mode cycle. So where they use space filling, then a different acquisition, a different acquisition, a different acquisition, and then space filling again, so that whenever they ask for a new step, they get a different experiment because they don't want to run the same one again and wait for the data. And so in the plots here, the mode cycle here on the bottom, from the bottom, the right one here, the mode cycle is plotted here in red. That one sometimes performs well because it is kind of cheating by using the bounds because of the space filling, because the solutions are of the 7 dimensions, like 3 of them are actually at the very extreme of the bounds. But the statement of the paper is that if you use the pending points version, so which is a paper from 2017, you don't have to do that heuristic trick of cycling and using space filling. You're just doing Bayesian optimization again, but you're not running the points that are pending. So that's why it's called pending points. So that's the confusion here. And the space filling is what they used, and this is published and everything. And it makes sense as a hack that did temporarily there when they build it. But they obviously, next time they were going to run this, they're going to use pending points. So that doesn't make more sense.
Yeah, just curious how you, because there are lots of space filling designs.
Yeah.
Like Sobel points, for example, and so on. So you can generate sequences of points that essentially have certain properties in terms of distances between points in multi-dimensional spaces. Yeah. But I'm just wondering how you choose this.
Yeah, so it's the original authors describe which space filling they used, and I think obviously for our simulations we also had to implement it again. But I don't know the actual specifics because that was done in a previous paper that we're trying to improve on. Yeah, I think that makes sense. Any more questions?
Thank you.
There's also a chat possibly online. That's what I was trying to do. I don't want to. How do I get to the chat?
Yeah, there's nothing on the chat.
Yeah. Okay. Sounds good. All right. So, well, thanks, Hao, for the presentation. I hope that that was, somewhat useful, and you learned something about Bayesian optimization, maybe some context. So I had a really good tour through your lab, and I learned so much about the work you guys do here. And so just as some context, so the self-driving lab is obviously a really annoying marketing term. It's simply just automation. The idea that's suggested there is also that self-driving, everyone will have a self-driving lab. I doubt it. So to build these machines, for example, what you see on the bottom left here took 2 years, and then they took 3 days to run all experiments. So question mark, does that make sense? So I think there's. Yeah, exactly. Yeah. So someone actually did try to answer the question, and they had a SDL set up, and it took 2 years to get results. And then they sat down. They were like, "Let me see if I can do this by hand," and they got it done in 2 months. So, there's moderation. There's some balance there, and I think you don't want to. Most people will never go full automatic. It just.
So you can see how to store in a complex multi-dimensional thing, and you could do a multi. Why not? Not really, yes, please.
Yeah.
You've got to spend $500,000 for that.
Yeah. So it is a budget question, absolutely. But I think at the end of the day, though, what I'm trying to I guess the key message is if you run experiments and you have to think about what to run experiments, at least now you know that there's another method. And if you can generate data, or you have high expensive information sources and smaller ones that go cheaper, it's something to consider. And so with the grant, we're basically, finishing up building software that helps you adopt these methods a little bit faster.
Of course, you could use this to drive your own manual search.
Yeah, which you should be doing.
Yes.
Yeah.
Well, but if you sit down and you plan your experiment, so I'll do this and the other. You might not use something to guide you, because I'd have gone for 20 on my first, but it turns out it's 18 or whatever it was. So if I'd gone for the obvious one, I'd miss it.
Yeah.
So you should allow yourself to be guided by what you would use.
It does also depend on the question is, right?
Yeah.
You're trying to answer with your experiment. So, for example, this is great for optimizing something, but sometimes you are actually trying to understand the mechanisms, right?
Absolutely.
Yeah. Yeah. That's exactly what I was going to say. It's because there are physical parameters underneath these systems that you may need. So, for example, if you look at those results, you can see parts of that search space are still very poorly described by the Gaussian process.
Yeah.
So you can say that those parts that are poorly described, they basically are unlikely to contain the optimal solution. Very unlikely to contain the optimal solution. So we stop. But the point is that if you're trying to understand the physical mechanisms of what's going on, it's not the greatest approach.
You can guide by something much better, which is that demonstrating yeast grows best at 18 degrees. Big clue, right? And that was straight.
Well, I love your optimism. Yeah. I guess also another important thing, for example, is if we look at these convergence graphs, these are obviously multiple runs. If you spend the money, let's say 2 years, you're gonna end somewhere, maybe slightly higher, slightly lower. But there's no guarantee that you will definitely be there because it is a random statistical process. And so like with that, I think like probably no one ever here will run an SDL. And I think probably no one ever here will like go completely closed loop. But I think if we can use this to, be guided and just get some ideas when you run out of ideas, maybe that would be useful as a base level.
Yeah.
And so I guess when we go to the pub now, it'd be, nice to hear what problems you have and whether that fits into that.
I believe there's some yeast products in there.
Yeah, absolutely. Yeah. Well, I'll be buying snacks. They have a good deal today. So that's good. Okay.
Cool. Thanks a lot. And maybe we can thank our speakers one more time. Yeah, and if anybody wants to join the club, feel free. I'll be there.
It helps to minimize the activity.
No, I'm thinking maximizing.
That's